All right. Good afternoon, everybody. So my name is Shihu. So it's right there. It's only 4 letters. Maybe it's quite hard to pronounce, but I think it's easy enough to remember. So right now I'm a third-year Ph.D. candidate in the smart construction and intelligent infrastructure system laboratory. Of course, I'm majoring Ph.D. in civil engineering. Of course, at NJIT, our department. Today I will be making a presentation related to emerging technologies and their applications in construction and civil infrastructure management. So this presentation may take around 40 minutes. It's got a lot of things to go through. I hope you guys will be enjoying this presentation. Yeah, so this is the outline of my presentation. I will just introduce myself a little bit more in the presenter background section, and then I will go to the introduction about the entire presentation, and then because in the introduction part I'm gonna go through some issues or challenges we're facing as a civil engineer. So then I'm going to present some solutions I proposed or my team proposed to address those challenges or the issues. After that, I would just keep 5 minutes available to do some Q&A. Right? So I'll start with myself. That's me. So I'm third year right now. I'm the graduate research assistant this year in the SCIIS lab. So I was the previous lab instructor for the MEC 237 strength of materials for the last academic year. So then go to my education. So yeah, I'm doing my PhD here right now. I got my master's in project management at Illinois State University. So focus on construction project management.
Oh, Illinois State University? Yeah. Where is this?
Illinois. So
yeah, I went to University of Illinois.
About 1 hour drive to the west, away from UIUC.
Oh, really?
Yeah, to the west, 1 hour.
Your photo is much younger.
Yeah, that was me before PhD. Okay. That's what people say, right? Before and after, you see the big difference. Yeah, of course, no, I did my bachelor's in hydrology and water resource engineering. It's under the civil umbrella, but it's more focused on hydrology and the hydraulics part. All right. So this slide shows some of my research focus. So my some research interests include the construction automation, robotics, and data sensing and analytics. So there might some concepts might be kind of new to you, but once I talk about something else, I will elaborate them one by one. Right. So my research areas are digitize and build asset management, smart construction workforce management, and structural health monitoring and the intelligent infrastructure systems. And some research outcomes so far already yield 12 journal papers, and even 2 more are under review. So on the 11 conference papers. So I also did some professional services. For example, I was the reviewer for 14 journals and 4 conferences, and I also have mentored or I am mentoring 10 students starting from high school all the way to PhD. Yep. Let's start go to the entree. Before that, there's some side dish, some terminology I want to explain it before we dive deep. First one, emerging technology, right? What's this? So there are innovations that are in the early stage of development or adoption, which means that some of them are still in babysitting. Some of them already in the market, but the early phase of it. Build assets, any physical objects made by humans, like buildings, or the tables, chairs, computers. All right, it's called a build asset. And digital twin, maybe you have heard of this concept, very often these days. So, what's that? Here it tells you, it's a digital model of a real-world physical object. So, I can create a 3D model of this chair, of this table, right? That's a twin of the actual, physical object. Or it's a process of it's a process with real-time data connectivity, right? Digital twin can represent a physical object or a process. That's Then go to structural health monitoring. It's a continuous or periodic assessment of structures to detect any changes or that may indicate damages, deterioration, or failure. So this is more related to the maintenance and operation side. And last one is sensor fusion. This concept is more from the electrical engineering or computer science domain. It's a computational method to integrate, the different data from multiple sensors, such that they can jointly give more information on the same object. One example. So Professor Shane is right now using a camera, right? And also it's getting audio. Camera can capture me, audio, my voice can also, you can use to identify me. If we fuse them together, it's still me. But you have two sources of information, so which can enhance your understanding about this object you are targeting. That's called a sensor fusion. You are using different sensors to get the same, the different information, but on the same object or same subject, right? All right, then let's go to the introduction right now. So as you can see, right, in our infrastructure systems, we have many structures, bridges, buildings, dams, roads, and rails, right? So on and so forth. So, but they are facing some issues or challenges in US civil engineering domain. What are those challenges? First one, this is the truth, because our infrastructure is aging or deteriorating. Second one is you can see, maybe you read the news like 2-3 weeks ago or a month ago, the hurricane, right, in Florida. That's related to the climate change and extreme weather events. They would pose threats to our infrastructure systems. The third one is we focus more on the construction side. So another challenge we're facing is we have a construction labor shortage. So we have these challenges, but as civil engineers here, what should we do? Right? So the first one, the aging infrastructure requires us to monitor the structure closely, and then take needed measurements to either to maintain the good, or end up we have to make a decision, we have to rebuild it. And then the second one is we have to for the existing already built infrastructure, we might need to enhance its resilience against those extreme weather events. Sometimes they cause low possibility, high impact events. It barely happen, but once they happen, it's gonna be devastating. It's gonna destroy everything. The last one is for labor side, because one of my research area is workforce management. It's how we can leverage or develop in technological or managerial solutions to increase the work safety, productivity, and also efficiency. Right? This is the challenges we're facing. And then the question is, can emerging technology help address these challenges? Right? If yes, what are those emerging technologies? How can we use them? Or how can they help? They are available, they can help. But we want to adopt them into our field. What are the challenges we are facing to adopt those emerging technology in construction and the civil infrastructure sector? So my presentation is going to focus on answering these questions. Right? Start with the first one. So this slide shows a bunch of emerging technology we have so far: digital twin, building information modeling, reality capturing, robotics, Internet of Things, big data analytics, AR, VR, virtual reality, or augmented reality. Sometimes people say mixture reality, MR. We also have artificial intelligence. Another example, you can see Professor Shane, he has one 360-degree camera. That's one reality capturing device. It's under this umbrella, reality capturing, and so on and so forth. And then before I dive into how we can leverage those technologies in our construction projects, I want to talk a little bit about the full life cycle of construction projects, right? We start with planning, and then we go to design, construction, operation, maintenance, and disposal. Right? You agree with me on this?
Okay.
Yeah.
Disposal.
Yeah, disposal. Yeah.
What is it?
Disposal. Let's say you build a bridge, so you're going to let's say it's aging, it's old enough. It's time to just destroy and rebuild it. So the process of destroying this old bridge is called disposal. You're gonna find it, but you still have this process still involve a bunch of activities. Who's gonna do it, right? How much it's gonna cost? How long it's gonna take? Those kind of things still have to go to the project management side. How to allocate resources and equipment, those kind of things. Yeah, disposal.
So dispose include the recycling?
That's a good question. So I think so. Right now we're talking about the decarbonization and the circular economy. I think recycling should be under disposal.
Mm-hmm.
Yeah, right. So then like in this life cycle, those emerging technologies, how we can use them, for example, for planning and design, we can use BIM software, right? BIM and BIM software, they are different. So for example, your tool like Revit, Navisworks, Civil 3D, those are called BIM software tools. So BIM, it's a process, right? It's a digitized process to that. So I want to mention this one. And then we go to design. For example, we have like a generative artificial intelligence, generative AI. There's something, for example, so far, let's say we're doing structural design. So we're gonna use software to sketch it, like a Revit or ETABS, all right, to sketch it by ourselves. After that, we're gonna go to do a structural analysis to say the stability, right? But this entire process, well, a lot of manual work there. But generative design, how can I do that? Let's say if I have like a structural version of ChatGPT, so I will tell the machine, I want to build like a 2-floor building with, let's say with 4 columns for each layer. What's the dimension of the column? You just speak to that tool. The tool return you something. It's gonna be a 3D structural design there. But it might not be exactly what you want, but at least you have something to start with. And then you just need to make some modifications, to change that, adapt that to what you want. So you can say this process is going to help you a lot. But the question is, who's going to develop this tool, right? So then there's something else, like a disposal part. Like for example, so right now people are starting using the demolishing robot to do that.
I think generative AI is more I think will be heard and more common and applicable to the design side. But in general, AI kind of tool can be also utilized in the operations and maintenance. Because especially structural, we do the inspection, right? The building falling apart, so maintenance side, we need to use the drone and investigate all the facade. And then using AI, and we can evaluate, identify each defect, right? So categorize and obviously evaluate.
Here, I just want to mention, right? This is some examples I mentioned. It doesn't mean that generative AI only works for design, no. So when we do like a predictive maintenance, you can still use generative AI. So generative is like you provide me something, I give you something like to generate what you want. It's not like deterministic. You give me X, Y, and I just give you a number Z. It's not something like that. So it's just like a little bit like technical. So I just mentioned that. Another example is digital twin. Not only used for maintenance or operation, you can also use for construction process if you want to monitor the construction process. All right. Then, what are the benefits of using those emerging technologies? The first one can help us to increase the productivity and efficiency. How? There are many. If the construction side, right, you're doing actual construction, there will be like a lot of repetitive tasks. So if we have to do that, how about we just let the machine do part of our job? That's going to help us, right? You can say that can improve productivity. And the second one is we use those technologies that are standardized. Standardized that help us to improve the work quality. So if the entire process only involves the human, our work, we cannot remove the subjectivity. Subjectivity end up would contribute to maybe the quality issue. But those emerging technologies are standardized. So the third one is can enhance the decision making and the planning. So those technology, for example, we use the predictive analytics. This type of analytics rely on data. So we get the pattern from the data, and then we use the pattern to inform decision making. So then you make a decisions based on some solid truth, instead of just do some subjective, decision making. That's what I mean. The fourth part is more for it's more about the business part. So if there's some companies that adopt these technologies that can enable them with greater adaptability and also competitiveness for construction firms. Let's say there's another example on the bottom right corner. So some customers or some guys from the construction firms, they wear the VR goggle to visualize the design part. So this kind of thing, you are gonna use a very good experience about what you want to say for your design. Sometimes you say a lot. Just show me. Then okay, put this on. You will see. Oh, I got you. So that's what I want to say here. All right. we can say like, we already know the emerging technologies. We know how it would help us. But what are the issues? Because I'm doing research. What are the problems or challenges we're facing to adopt them into our civil engineering domain? So there are 3 challenges. Of course, there are more. The first one is the gaps between civil engineering domain knowledge and the emerging technologies for enabling domain-specific application. Let's say we want to only focus on inspection of bridges, but you want to leverage drone, LiDAR, camera, those kind of things, right? Like civil engineer don't produce LiDAR, don't produce the camera, but we use them. But how can we use them good in our field? When we're doing inspection, let's say we want to find out the cracks on the pavement. They give you camera, alright, you use it, but how can you identify the crack, quantify the crack, and also localize it? So that's the gap we have to fill. The second one is there's always a continuous demand of cost-effective, user-friendly, and adaptive solutions to data sensing, analytics, and the intuitive visualization. So you can see the reality capturing device right here. Can we make it cheaper? Right? That's what I mean, cost-effective. Second one, user-friendly. So can that do only one mode, or there are multiple modes I can choose? That means adaptive, depends on your needs. The third one is of course, adaptive as well. The third challenge is going to be low interpretability of AI in predictive analytics. So right now, mostly the AI right now, it's just a black box. You put something there, and you get something else, but you don't know what's going on inside. So there are another ways how can we increase the interpretability? That's basically the challenge we're facing right now. All right. But my topic today will be focused on the first 2 challenges. Challenge 1 and challenge 2. Challenge 3 also I did some work there, but I don't think I can finish everything just within maybe 40 minutes. So I'll focus on the first 2. So the proposed solutions for challenge 1. Knowledge gap there, we don't know how we do that. We read, we learn, but then we can find out the pattern. Then to tell the people, if they want to do research in the future, what they should focus on, what they can do. So the first one is to conduct a systematic review on the use of emerging technologies in the civil infrastructure sector. So for this one, the work I did was we focus on the robotics. So here just some results. This is that. I start with the application side. So application of the unmanned ground vehicle, UAV. So this is a taxonomy. It's just a concept, and there are some category. So they are used for site safety management. So for example, water spraying. This is one research I did last year. Is we deploy a drone with a thermal imaging system, so it can capture the environmental heat. So because for OSHA, they have some standard for the heat stress. So once the heat stress reach 88 degree Fahrenheit, you can take measurements. How? For the project I did was to trigger the water spray functionality of the drone. The drone would also carry a small water tank. Once detect that in this region, the heat stress is above 88 degree Fahrenheit, and then it's kind of like a spray water. Of course, this 88 degree Fahrenheit is not just a temperature. It's they have some standard. It's a well above temperature. So you have to think about something else like humidity, like radiation, those kind of things. So then I'll give you a overall evaluation score. You're gonna use that to compare with the existing criteria to say what you should do. Right? That's just one example. The drone has also been used for wireless communication, but that's kind of far away from what we were doing. For disaster management assessment, every time after for example the hurricane in Florida, so some community would be submerged by the water. But how much area got submerged? So you deploy a drone, all right? You take video footages, all right? You have the footages. How are you gonna deal with those video footages manually? That's the regular way we do that. But there may be not maybe it's people have already done computer vision to automatically identify how much area got submerged and also assess the severity. Yeah, that's just an example. And then this might be very interesting for you, for you folks. It's the distribution of the drones, different type of drones in civil infrastructure sector. So as you can see here right now, the quad rotor, this is the mostly commonly used one. This is something you can take away. And then there are also some other drones like the helicopter, the hexacopter, copter, or like a octocopter. People sometimes call that just 4 rotor, 6 rotor, like an 8 rotor drone. Yeah, that's just their terminology. Last one is fixed wing. One question I ask you folks, why do you think the quad rotor is the mostly used one?
Because it's probably the most cheapest to afford.
Okay, that's because think about the cost.
Yeah.
Anything else? Think about the application, right? You're gonna figure what do we want to use that for. If you only want to use this to take images or videos, right? For rotor is good enough. But the camera is light, it's lightweight, right? But if you want to use that to, let's say, carry like a tank of water to cool down the local environment, maybe you're gonna need the 8 rotor one, right? Because higher payload.
More popular now, drone taxis and drone. What is that?
Last mile delivery.
Yeah.
They would need like a bigger one. They would need like a bigger one with the higher payload.
Yeah.
It's just like something you can see because this figure it's from the existing literature. So it's from my research. We went through like more than 100 papers, and then we find out that the pattern, and then visualize like this way. And another example is the application of unmanned ground vehicles. It's like the rovers, right? Like 4 wheels, 3 wheels, or even like more than 4. And then this one has been used like very widely. So they're used for like construction related activities, like the brick laying and the paving. They can install a robotic arm on the rover, and then the rovers can navigate, go to grab the brick, and then the arm is gonna place it there and put a motor.
Our architecture department have some robot and they test it.
Yeah.
Maybe.
That one I didn't taste that one, but I visited the big robotic arm before. That one's quite huge.
Yeah,
that's quite huge. That's just some example. And also there are something else. The health facility management. That's related to like the operation in the life cycle. So they go to detect like the contaminated surface. It's like this. They use like the camera there, and also the UV. It's a UV sensor. Yeah, UV sensor to do that automatic identify this part. In the hospital, they are still identify the high chance there's still some bacteria or some other virus there. They come somewhere here. It's distorted, but it's distorted, but it still represent the same information. It's the same thing. It's just it's just like about how the project, the captured objects when they want to represent it. Yeah, it's the same information. Another thing is like this distorted one has more information because it can capture part of the ceiling, but this one's gonna be a little bit less. That's also the difference. But no matter how, this system it's adaptive. It depends user. You want to get the distort one, use option 2. You want to get the first one, option 1. Yeah, and if you don't want to get a 360 degree, you want to only get 270. That's still also possible. You just need to disable one or 2 of the cameras. So that's I mean like this system has high adaptability. This is one. Yeah, this is the video. So here this camera can achieve like 11 frames per second so far. So this is like our lab. So I was walking there. You can say, right, it's quite smooth. Yeah, it's a video. I didn't talk about application for this one yet. So this is basically we're building foundation. So above this, we're gonna talk about application. So before that, I want to talk about like the robotic 3D colorized mapping system. You understand it? Very simple, 3D scanning, right? 3D scanning of our building environment. Just understand this is that. But behind this one shows like the overall workflow. So what do you need to do? Still hardware design, and then robotic prototyping, and then you're gonna test the robot in the field. After that, over it's good. You collect the data. What data to collect? Point cloud from LiDAR. Panoramic RGB image is from the 360 degree camera system. And then the IMU, it's motion sensor. When you move, that can detect the change of your motion. Yeah, how many degree, angle got changed, something like that. And also, if you want to localize where you capture the data, you're gonna use the global navigation satellite system. So this is like a more general version of GPS because this system includes the European system and also the Chinese spatial system and also US GPS system, right? And then once we reach there, we're gonna categorize the point cloud and then georeferencing that, and then you just register point cloud to get a map. It's kind of like conceptual, but I'm gonna walk you through once I move on. And here, this is like the robotic platform right here. This is the base. Provide the mobility of the entire system. This is the onboard computing device. This one would be used to control these sensors, and at the same time also control the motion of the robot. So basically, this is the brain of this entire system. And this is a LiDAR. This is the Oyster LiDAR 128 beam. So to get a 3D representation of the environment through a set of dots or points. It's kind of hard to imagine that. You can understand that when we represent a 3D space, we can use edge, surface, right? But if we do like a sampling, from that, maybe we just need like a part of the information. It's gonna be some dots. Roughly, we can still represent the same thing. That's called point cloud. It's a cloud of points. Yeah, but point cloud only gives us the geometric information, but we don't have the context information because we know that our eyes can vision the geometry and also the colors. Our data together, so you will get a colorized map. That's why I mentioned the concept sensor fusion before, right? So this is the 360-degree camera system, but this one is more advanced because I made some upgrade to that. Previously, it was like 6 cameras in total, right? 5 on the side. Right now, it's only 4 on the side, but still can give us like the panoramic view, 360 degree. This end up reducing the cost to develop this system. That's the benefit out of that. This is one example of the colorized point cloud. This is a 3D model of my lab. So I'm sitting here. It's my computer. This is a closet. So it's a video clip here. This is only one frame of that because this is ongoing research. So I'm going to expand the scale. Starting with a room, as Professor Shen always says, start with something small. And then you go to big. So I start with one room. Next step is going to be the entire floor. And then go to the multiple floors of the entire building. And then even move to outdoor. So to go to large scale, like even go to, yeah. And then the second solution for the challenge number 2, it's the novel digital twin frameworks for application. This can be heavily about application. The first one is the digital twin framework for indoor environmental monitoring. This one is related to the facility operation, right? You want to monitor the indoor environment. Let's say the thermal comfort. You feel hot, you feel cold. I know most of you guys would complain, winter too cold, summer too hot. Right? But how can we inform the facility manager? It's time, just drop the temperature, please. It's too hot. This is one example. And then we go to the other side. It's like the structural health monitoring. This is gonna be related to structural engineer. Very. You're gonna let's say monitor the structure behavior under certain loads. Is that within the safety range or above that? But how can we know this? Unless we go to Mayor, right? But we don't want to manually, to do the manually, go to the site. But how can we automate this? That's basically the core behind this digital twin. There's going to be 2 application scenarios. I will start with the first one. This is kind of like complex, so don't be scared. It's just like the foundation behind that to build this system. So make it easy. It's like we develop a ground vehicle. And then we put some environmental sensor on that. And then this vehicle is tracked by an indoor positioning system. So then we know where this robot is. Basically, we know which region this robot is sensing, right? And then after that, we get the environmental data. Then we use that to assess the environmental condition, and then find a way to visualize that in BIM software. That's a quick summary about this. Yeah, it looks kind of scary, but this is the robotic platform right here. It looks like a little. This is a Thunderbolt 4 ground vehicle. It looks like a little bit. If you just remove, the top part, it looks like a cleaning robot. Yeah, something like that. And this is the sensing unit right here. And then because we deal with IoT as well. And then this is like the ESP32 board to basically to self-localize the robot. And these are some other sensors. This one to detect a PM 2.5 and a PM 10, and this one to detect CO, and also CO2, those kind of things. Yeah. So because it's a system, it's a big system, and another advantage of this system is that the robot has like a full level of autonomy. Once we just specify the path, the robot is gonna go all by itself. But of course, the condition is that we're gonna make sure the door is open. Otherwise, the robot cannot enter that room. Yeah, that's the thing. Maybe in the future, we're gonna make a bigger robot with a robotic arm can open the door by itself. And people have been doing that. Yeah, this slide shows the autonomous navigation. So I just show you some example. We just need to specify a sequence of waypoint in this map, 2D map. 1, 2, 3, 4, and then the robot is gonna go by itself. Oh wait, then come back here. Let's see the final product. This one represents the region where the robot is, and also the color represents the air quality index. So starting from 0 to 500. Of course, the lower the better. Usually below 100, we're fine. And so here in my lab, at that time it was under 100, so it was good. Yeah. So when the robot was moving, you can see as everything has been done in BIM. It's been this is
Revit. Yeah.
Yeah, in Revit. Platform. This is in Revit. So it's in Revit. So we have the knowledge on this, and then we apply that. We adapt some new things to this one for facility management. So when let the decision maker know this, they know at least where the problem is, because the information from the positioning system, and then they also know how terrible it is by the index number. Yeah, but the question is, you need the model. You need a 3D model.
Yeah, the architect, or we can build that, or architect can build it.
Yeah, but you remember this one?
Yeah, you can scan it.
Yeah, you can scan it also. Mm-hmm. But if you don't have access to the original 3D model, but you can scan it. But even you have the original model, you might still need this system. Well, if you focus on inspection side, you want to detect the defects of the structure, cracks, spalling, those kind of things. You detect them. How can you visualize it? Are you gonna make a change to the original one? Maybe you don't want to do that. Maybe just use scanning one. I can run machine learning model, detect it, and then visualize it. I just deliver this scanned version, and then you can use this for your decision making and the following planning things for maintenance. Yeah. Let's move to the last topic. It's gonna be the digital twin framework for real-time structural health monitoring. You might be very interested in this one.
Yep.
Yeah. So for this case, it's we develop a very small prototype. It's made of aluminum. It's just structural frame with four columns and 8 beams. So it's kind of small. And then we installed a strain gauge sensor on one of the beam, and also we install another distance measurement sensor to measure distance in order to quantify the deflection of the column. Yeah. So basically, we're gonna use sensor to collect the data. After that, we're gonna transmit the data to BIM software, and then find a way to visualize it. But the innovation behind this methods that strain gauge sensor can only measure the strain at one position. Do you agree with me? If you just use the strain gauge sensor, not the fiber optic sensor. But then, can we use only one data point to visualize the different structural behaviors of the entire column or the entire beam? The answer is yes, but how to make this happen? You will see, all right? Keep this in your mind. This is one. The second is how fast you can visualize the structural behaviors in beam. Let's continue. Starting with the prototype construction. Just some like aluminum columns and beams. We got this one, and then we went to the makerspace. This is my collaborator, and also this is like a very like experienced. I think he's a student also, but he was helping us to do the welding in the makerspace. End up we got this frame. We got that like the aluminum frame, and then we installed like the strain gauge sensor at the bottom of this beam. So attached on the surface with glue. Then this is basically the beam number 1. It's the one of interest, and this is the column. So, but we're gonna find a way to stabilize this frame and then apply the load. This load include the point load and also the uniform load. Yeah, but for the column, we will try to bend. Yes, please.
Is that load also included as well?
No, we just do some prototyping. Yeah, it's like we want to apply some load, we see the string, and then to visualize it. Yeah, that's basically what we did. That's a very good question, right? And I mentioned like use one measurement to color like to capture the structural behavior of the entire beam or column. This is how we did it. We use the right. This is very it's very like familiar, right? A bending moment diagram. But this is what we have to guarantee that we're not gonna like permanently deform this column or beam. No, we're not gonna like deform this beam. We can. If you deform that one, this one doesn't work, right? It's gonna be within the elasticity region. That works. But once we know that it reached there, we're gonna know, all right? We cannot do more. It's very close. But anyway, we use that. Basically, you use this method. Look, sensing data, domain knowledge. That's how we create the gap, to fill up the gap. This is domain knowledge. The emerging technology like IoT is from other field. And then we have our goal is to make them work together to serve our need. So we get that, and this one we can use this one to do the sensor data interpolation. Once we can interpolate data, so then we know the strain. Let's say we focus on right now only on strain. Then we know the strain value almost at each location. Yeah, that's just some innovation like we did for this research. But what we did is like we partition the entire beam into different segments because it's impossible, to deal with infinity segments. So we just choose like some of them to say just to prove this concept works. This is another exciting thing here. So once we stabilize that, we apply a load at the mid-span right here. You can see here, this is strain value, but of course the maximum is 0.02. When you apply a load, then you will see like the strain at a different location, only based on one sensor measurement. Yeah, but of course, in actual world, the strain won't like disappear so quick because we just do some experiment to test the entire system, make sure it works. If like there's constant load applied there, of course the color gonna keep there like maybe for a while. If bigger load apply, then you will see a bigger strain, something like that. And then once we reach here, we will apply a point load to stretch this entire architecture. So then here we can see some deflection, but this deflection is basically for this point. How much this point deflected towards the right hand side. And then you will see the color got changed here. Yeah. So yeah, that's basically my research. So I would like to thank the NSF Innovation Corps and also NJIT for providing the financial support to do different research. And I'll be very happy to address some questions you have.